First of all, what is a planet? Well, that depends on the definition that one is using. Currently, one of the most influential definitions was created by the International Astronomical Union members, and then it was voted at an organizational scale as the official definition in 2006. The motivation for creating this definition came about because suddenly, after the year 2000, there was a sharp increase in the number of objects found in the size range of Pluto. All of them were found to be beyond the orbit of Neptune. The most prominent ones were Eris, Haumea, and Makemake, which were discovered by 2006. Because all of those objects found were even below the size of the Moon by quite a bit, that also led to a desire to draw a line between a planet and a dwarf planet. But interestingly, despite the small size being the primary characteristic of these newly found objects, the definition which was accepted for a dwarf planet has no mention of size. It only tries to indirectly hint at size, and ultimately because of that, it fails at drawing a simple and clear line between small celestial objects that are round and large ones. It is mentioned in the IAU page regarding the definition that the team found several objects that did not resemble any of the 8 planets we consider today, but were large enough to be compared to Pluto. These discoveries prompted astronomers to ask the question, what constitutes a planet? The team being referred to here is the one that discovered Eris, Haumea, and Makemake. Regardless, the quote from the official site directly mentions size, large enough to be compared to Pluto. So size was obviously considered when thinking about what constitutes a planet. So then it is unexpected that the definition voted for by the IAU has no direct mention of size, not even mass. At least that would be more closely related to size. Instead, what the IAU did was look at the orbits of these newly found objects, and they saw that compared to the orbits of the 8 regular planets which orbit the equatorial plane of the Sun, these newly found objects have messy orbits that are highly tilted in relation to the equatorial plane. So the definition for a planet that got voted for has 3 conditions that an object has to fulfill in order to be classified as a planet. A. Is in orbit around the Sun. B. Has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape. And C. Has cleared the neighborhood around its orbit. Pluto, Eris, Haumea, and Makemake fit the first 2 conditions, but the third condition is what disqualified them from being just planets and classified them as dwarf planets. When we take a look at their orbits, we can see that they are pretty messy. They somewhat have an object that is relatively large, that is also somewhat in their orbital path, that is in their orbital neighborhood, and that's what disqualified them. The massive problem with this part of the definition is that out of the sextillions of planets out there, there are certainly planets that are about the size of Neptune, and those could, for example, have a Jupiter-sized planet close to their orbital path, meaning that those Neptune-sized planets don't have a cleared orbital neighborhood. So according to the voted IAU definition, those Neptune-sized planets don't fulfill one of the conditions that dwarf planets also don't fulfill. However, on top of that, they also don't fulfill the other condition, which is must be in orbit around the Sun. Obviously, none of those Neptune-sized planets orbit the Sun. So to give some perspective on what is going on here, on the left is Mars, and on the right is a Neptune-sized planet without a cleared orbital path. While Mars is a planet, that Neptune-sized planet is not a planet, according to the IAU definition voted for. So this is just one problem with the IAU definition of a planet and a dwarf planet. The dwarf part of the definition is largely ignored. It is only trying to vaguely point at size. What is interesting is that this is the quote that was chosen to be put on the official IAU page regarding the definition of a dwarf planet. We wanted to avoid arbitrary cutoffs simply based on distances, periods, magnitudes, or neighboring objects. This is a quote by the IAU chair of the Planet Definition Committee. This is really puzzling. It is clearly stated that the definition they want should not rely on arbitrary cutoffs, and the examples of arbitrary cutoffs are listed. And yet the IAU voted for the exact arbitrary cutoff that was said should be avoided. The official definition voted for clearly states that neighboring objects do influence whether or not something is considered a planet. But the problems with this definition don't end here. When they were creating and voting for the definition, it seems like they were only thinking of the solar system. The proof that they were only thinking of the solar system is the fact that the definition which was voted for says that a celestial body is a planet if it is in orbit around the Sun. So this definition doesn't count planets that don't orbit the Sun as being planets. Obviously a bit ridiculous considering that we know that there are planets orbiting other stars. So then, in this page, without acknowledging the problems, they try to modify the definition by saying that more generally, a planet orbits its host star, just as the Earth and Jupiter orbit the Sun. So they saw that the voted for definition wasn't universal enough and changed it so that it says that a planet orbits a star. But this also has weird entailments, because some planets just get ejected out of the system in which they formed, and they start wandering around without orbiting any star whatsoever. Those planets also don't fit the changed IAU definition of a planet. They also changed has cleared the neighborhood around its orbit to say must have an important influence on the orbital stability of other objects in its neighborhood. These sentences sound like they mean similar things, but they don't. An object could have an orbital path that is not cleared, and yet still have an important influence on the orbital stability of the other objects in its neighborhood. For example, Ceres in the asteroid belt has an important influence on the orbital stability of other much smaller objects in its neighborhood, and yet Ceres does not have a cleared orbital path. So Ceres fulfills all of the conditions for being a planet according to the changed definition, but it doesn't fulfill one of the conditions voted for initially. Another attempt at fixing the definition is when they changed the second part of the definition from has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape, to is large enough to be mostly round. Large enough to be mostly round. Objects can be the size of typical asteroids and yet be round. Is that large enough? As for hydrostatic equilibrium, it is frequently said to be a condition for a planet and a dwarf planet even outside of the IAU definition. So the following criticism targets other definitions for planet and dwarf planet which have that condition. But to be fair, this is the only part of the IAU definition that is, to me at least, somewhat reasonable, in that celestial objects that are in hydrostatic equilibrium are round, and they are typically larger than about 300 kilometers. And maybe that was what was meant by large enough, but they didn't mention that. So hydrostatic equilibrium as a condition is trying to reference relevant characteristics when it comes to planets and dwarf planets, which is their round shape and size. But yet again, hydrostatic equilibrium is doing that indirectly. Although not as indirectly as clearing the orbital neighborhood condition, the indirectness still inevitably leads to strained entailments, because there is a blurry correlation between being in hydrostatic equilibrium and being round. In other words, not all round celestial objects are in hydrostatic equilibrium. Hydrostatic equilibrium is achieved in objects when gravity, the force pushing inwards, balances internal pressure, which is the force pushing outwards. Then that creates round celestial objects. However, the rotational speed of celestial objects also acts outwards, so it counteracts the force of gravity, especially as you get closer to the equator. With that, because round celestial objects in hydrostatic equilibrium are typically rotating, they are also all to some degree oblate, meaning a bit shorter from pole to pole compared to the equatorial length. However, when the rotational speed gets really intense, that can then counteract gravity in certain cases enough such that the object becomes extremely elongated. For example, there is Haumea, the largest known extremely elongated object. It has a rotational period of only 3.9 hours. Such an insanely fast rotational speed made it bulge at the equator. However, according to one important study on the topic, Haumea is in hydrostatic equilibrium, so it appears that its shape is fluid enough such that it adjusted to the rotational speed that it has. Interestingly, according to one of the reports that the IAU put out, Quasar is a dwarf planet, and yet despite that, it is far from being in hydrostatic equilibrium. This shows how even the IAU, at an organizational scale, does not take seriously their own definition which was voted for. Now let's take a look at why Quaoar is far from being in hydrostatic equilibrium. So we have Quaoar and Haumea, which are both bean-shaped. For Quaoar, the mean diameter is 1,084 kilometers. For Haumea, it is 1,560 kilometers. Haumea needs only 3.9 hours to complete a rotation around itself. That is close to being in line with the shape that it has. However, Quaoar needs 17.5 hours to complete a rotation, which is much more in line with the rotational period of Makemake and Gong. With that, if Quaoar were to be in hydrostatic equilibrium, then its shape would respond to the rotational speed and adjust such that the shape resembles more the much less elongated shape of Makemake and Gong. But the shape of Quaoar just didn't adjust, and that is exactly because it is not in hydrostatic equilibrium. The reason Quaoar currently has an elongated shape is because in the distant past, its rotational speed was closer to that of Haumea. Then, however, it solidified into that elongated shape and essentially got stuck there, unable to respond to the slower rotational speed that would later come. Now, does it really then make sense to disqualify Quaoar from being a dwarf planet just because it isn't in hydrostatic equilibrium? To me, it simply doesn't. It's in the size range of dwarf planets, and it is round, although in an elongated way. So visually, it fulfills two of the most iconic aspects of dwarf planets. So the problem with hydrostatic equilibrium is that it is only indirectly trying to hint at size, and that then leads to weird situations where objects as large and as round as Quaoar get disqualified. There is another example of an object in the dwarf planet size range that would get disqualified. Iapetus is a moon of Saturn. It has a mean diameter of 1,468 kilometers, similar to Makemake, and yet Iapetus is far from being in equilibrium according to one study. That is because its shape is in line with a much faster rotational period of 16 hours, and not 73 days that it has now. Meaning, according to its rotational speed today, if Iapetus were in hydrostatic equilibrium, then its shape shouldn't be as elongated. This means that Iapetus solidified into its somewhat oblate shape during a period when it had a rotational period of 16 hours. Then its rotational speed slowed down, but now its gravity isn't strong enough to make it less oblate. So then, because Iapetus is far from equilibrium, if it were to just orbit a star or the sun instead of a planet, then it wouldn't even be a dwarf planet according to the IAU definition and some other definitions that include hydrostatic equilibrium. And yet, there is certainly a massive number of Iapetus-like objects orbiting stars. Apparently, none of those are even dwarf planets. Besides hydrostatic equilibrium condition disqualifying objects as large as Quaoar and Iapetus, it can also do the opposite, which is qualify objects that are ridiculously tiny. Probably one of the smallest objects currently that is close to being in hydrostatic equilibrium is Methone. It is a moon of Saturn with a mean diameter of 3 kilometers. It has a very smooth and unusually round shape, and it's not like this image is super blurry. The resolution here is 29 meters per pixel, and the reason for this shape, according to one study, is because it is close to having an equipotential surface, essentially meaning it is in hydrostatic equilibrium. Possibly the reason Methone achieved such an exceptionally smooth and round shape is due to its exceptionally low density of 0.3 grams per centimeters cubic. For some comparison, the density of water is 1 gram per centimeters cubic. So this is probably one of the least dense celestial objects found in the solar system. And this super low density implies that Methone is a highly porous rubble pile moon that is also highly fluid. That's also why it entirely lacks craters. It just quickly erases them. Now, considering that the study does consider this object to be close to hydrostatic equilibrium, that then does mean that it would potentially be a dwarf planet if it were orbiting the sun or a star according to the IAU definition. And considering how many objects there are out there in the universe, it is quite possible that there are many objects like Methone orbiting stars. So apparently those asteroid-sized objects could easily be dwarf planets, while Quaoar and Iapetus-like objects aren't. Besides Methone, Aegean, and especially Pallini, another 2 moons of Saturn, also appear to be close to hydrostatic equilibrium. They are also similarly sized to Methone and are probably highly porous rubble pile moons. One interesting thing is that a mere water droplet in space achieves hydrostatic equilibrium, However, on such a small scale, it is not gravity balancing internal pressure which causes equilibrium, but rather it is surface tension balancing the internal pressure which causes equilibrium and turns water droplets into spheres. Surface tension is a property of liquids where molecules tend to stick together and minimize their surface area. On much larger scales, gravity starts to have more of an effect in shaping objects. For example, Haumea. It is located in the asteroid belt and it is round but barely. Now, a large part of the reason it got its round shape is likely because of a powerful impact that liquefied a large part of Haumea, essentially turning it into lava. Because the material strength got reduced so much, that then allowed for Haumea to turn into a sphere. Surface tension probably had a significant effect in terms of shaping Haumea, but without a doubt, Haumea's gravity also played a role. Haumea is not a water droplet. It has a mean diameter of 435 kilometers and a mass of 87 quintillion kilograms. Its own gravity influenced the final shape during those crucial moments when there was a bunch of lava. However, now that Haumea is solidified, it is hard to say whether or not it is in hydrostatic equilibrium. So besides hydrostatic equilibrium as a condition leading us to bizarre entailments where asteroid-sized objects are dwarf planets and round dwarf planet-sized objects aren't counted as dwarf planets, it is also very hard to even determine whether or not an object is in hydrostatic equilibrium, both in terms of how far away it is from equilibrium and also in terms of how far away is too far away for an object to be counted as being in hydrostatic equilibrium. Pretty much all celestial objects, to some degree, are away from perfect equilibrium. This is similar to how there are no perfectly circular orbital paths. Celestial objects just deviate more or less from that perfect circle. Now, determining whether or not celestial objects are in hydrostatic equilibrium is an interesting scientific question that could provide scientific value. But because of the reasons already stated, to me it just has no place as being a part of the definition of a planet and a dwarf planet. So I am rejecting every single condition in the voted IAU definition for a planet and a dwarf planet. So then what counts as being a dwarf planet and a planet? To me, being a dwarf planet is exactly about size and also shape. It only makes sense given that dwarf refers to something that is relatively small, so it refers to size. So then, according to me, the definition of a dwarf planet is approximately round celestial object that has a mean diameter between about 300 kilometers and about 3,000 kilometers. Then the definition of a planet is approximately round celestial object with a mean diameter greater than about 3,000 kilometers. Both of these definitions also exclude black holes and stars. It really only makes sense that we refer to size when we use a size designator such as dwarf, so a size range is provided. And the reason I am acknowledging that a definition of a dwarf planet should exist is probably because it is quite useful to distinguish between these large main planets and smaller ones, especially because it is possibly the case that the difference in orbital patterns between dwarf planets and planets is replicated frequently in other systems. That's why the maximum proposed size for a dwarf planet is about 3,000 kilometers. Below that, it is possible that we can typically expect messy orbital patterns. And why is about 300 kilometers the minimum size for a dwarf planet? Well, because generally, above 300 kilometers is when objects start to get more and more round. Now, for objects that are about 300 kilometers, it is true that it is probably rare to find some that are fully round, but they are almost certainly out there in the universe. Then from 300 kilometers all the way to 1,000 kilometers, objects get significantly more round. After 1,000 kilometers, it is nearly a certainty that a celestial object is round. Of course, there are also round objects that are well below 300 kilometers. We have Methone. But a general tendency of objects becoming significantly more round starts at around 300 kilometers. So because this definition of a dwarf planet has a size limit, it just doesn't run into the problem of calling tiny 3-kilometer Methone-like objects as dwarf planets because they are round and close to hydrostatic equilibrium. And it also doesn't run into the problem of calling objects as large and as round as Quasar as non-dwarf planets. One potential objection to these size ranges provided is, what about round objects that are, say, 299 kilometers across, or 3,001 kilometers across? do these not count anymore as dwarf planets? Well, according to the exact definition provided, they could. The definition says about 300 kilometers and about 3,000 kilometers. So it does give some room for objects a bit outside of the range to be included. And it is true that could give a bit of a problem in terms of categorizing objects that are right a bit beyond the approximate limit. But those cases are going to be very rare, especially for round objects that are, say, 299 kilometers across. We don't know of any currently, although they almost certainly exist somewhere. And as for objects that are, say, 3001 kilometers and round, those are not going to be as rare, but classifying them won't be that big of an issue. And if it ever does become an issue, putting a hard limit is always an option for the sake of convenience. Another potential objection to the provided definition of a planet and a dwarf planet is as to what counts as being round. One might think of Haumea, a bean-shaped object, as not counting them. But the thing is, although it isn't exactly a sphere, it is still a very round object. It is just round in an elongated way. So the definition covers objects that are round and elongated. But then, how exactly round should an object be in order to be considered a dwarf planet? Well, just like how the size ranges are approximate, so can the roundness be approximate as well. Just because there isn't an exact line drawn doesn't mean there isn't a noticeable difference between irregularly shaped celestial objects and round celestial objects. And again, if this ever does become an issue, then a hard limit in terms of what roundness counts can also be created. So there is some vagueness in the definition, and if that ever does become an issue, it can just be updated in order to exclude any vagueness for the sake of convenience. Same is true for mean diameter. Also, if one finds an issue with vagueness, then they would also need to find an issue with the IAU definition. So clearing the orbital neighborhood is incredibly vague, and hydrostatic equilibrium as a condition for a dwarf planet and planets suffers from the exact same problem. There isn't an exact line beyond which one can say that an object is certainly in hydrostatic equilibrium. All objects deviate more or less from perfect hydrostatic equilibrium. But on top of vagueness in terms of how far is too far away from equilibrium, even just determining how far a celestial object is from perfect equilibrium is very hard to do alone. Another potential objection to this new definition for a planet and a dwarf planet is what about moons? That is, satellites. Well, the definition could easily exclude moons, but what's the reason to not exclude them? Well, that is pretty simple. Visually, they can be identical to planets in two key aspects: size and shape. Because of that, they can be just as interesting or even more interesting than planets. For example, Titan, a moon of Saturn. It is even larger than Mercury, but besides that, it is also way more geologically active. Unlike Mercury, it has a thick atmosphere, and on top of that, on its surface, it has lakes made out of liquid methane and ethane, something that Mercury obviously doesn't have. So given that Titan is even larger and more geologically interesting than Mercury, it is a bit surprising that giving it the status of being a planet isn't considered all that much. It is especially puzzling that finding out that Pluto is smaller than our moon led to a great desire to demote Pluto, but finding out that Titan is larger than Mercury didn't lead to much of a desire to demote Mercury, or at least give Titan the title of being a planet. Another reason for giving round objects larger than 3,000 kilometers the title of being a planet is because, for example, both Pan and Titan are moons of Saturn, and yet Titan has way more in common with the planets such as Mars than it does with the moon Pan. However, the term moon is a useful piece of information, so what I am proposing is that an object can be both a planet and a moon at the same time. So Titan is a moon planet, or a satellite planet. Besides Titan, Jupiter's moon Ganymede is also larger than Mercury. There is also Callisto, another moon of Jupiter that is similarly sized to Mercury. In total, according to this new definition, there are 6 moon planets, and that does include our moon. And just like there are moon planets, so can there also be moon dwarf planets. So those are moons that are round in between 300 and 3,000 kilometers. Now let's establish as to what counts as an asteroid. To me, asteroids are characterized both by their irregular shape and their size. Because of that, I define an asteroid as all celestial objects that have a mean diameter less than about 300 kilometers and all celestial objects with a mean diameter greater than about 300 kilometers that are irregularly shaped. So because of this definition, Vesta is classified as an asteroid because of its very irregular shape, despite being 525 kilometers across. And Methone, despite being very round, would still get classified as an asteroid because it is about 3 kilometers across. Also, yes, just like how there can be moon planets and moon dwarf planets, so can there also be moon asteroids, according to this definition. So here are all 3 definitions that I created for the purposes of my future videos. They are simple and can pretty easily draw a line between different celestial objects in the vast majority of cases. Now, you can disagree with using these definitions, but despite that disagreement, let's be honest, you can very easily understand what is being talked about when I say something is a planet, dwarf planet, or an asteroid. Another one of the most famous definitions for a planet was proposed by Alan Stern, a planetary scientist involved with the New Horizons mission, which got us the up-close photos of Pluto. In 2002, along with his colleague, they proposed this definition. So a planet is a planet when it fulfills these 2 conditions. 1. Be low enough in mass that at no time, past or present, can it generate energy in its interior due to any self-sustaining nuclear fusion chain reaction, else it would be a brown dwarf or a star. 2. Be large enough that its shape becomes determined primarily by gravity rather than mechanical strength or other factors such as surface tension and rotation rate, in less than Hubble time, which is about the current age of the universe, so that the body would, on this timescale or shorter, reach a state of hydrostatic equilibrium in its interior. With regards to the first condition, I do like it. Unlike the IAU definition, which was proposed much later, this one as its first condition tries to establish that stars are not planets, and it does so in a clever way by specifying that below a certain mass point, we just get planets. So this also points at another problem with the changed IAU definition. A star orbiting another much larger star is considered a planet. That is, if it has an important influence on the orbital stability of neighboring objects. And it is very easy for a star to have that influence. So according to the changed IAU definition, there are a bunch of planet stars out there. This definition by Alan Stern and his colleague, however, does not have that problem. Still, the second condition for this definition is where I do have a problem. 2. Be large enough that its shape becomes determined primarily by gravity rather than mechanical strength or other factors such as surface tension and rotation rate. A massive problem with this is that it is very hard to determine whether or not an object's shape is primarily due to its gravity or due to other factors. The line is just extremely blurry. For example, let's take Haumea. Its shape is determined in huge part by its incredibly fast rotation rate, but its gravity also played a role in giving it a smooth appearance. But still, without a doubt, the rotation rate massively contributed to the shape we see today. Its fast spin caused it to bulge on the equator massively. So then, in the case of Haumea, which one contributed more? Gravity, or rotation rate, or its mechanical strength? Well, that is all extremely unclear. It should be noted that this definition was formed in 2002, and Haumea was discovered in 2003 or 2004. This second condition in the definition also gives Hubble time, which is the age of the universe, meaning about 13.7 billion years for an object to achieve hydrostatic equilibrium. But it should be emphasized that we just can't tell which object will reach that state. That is nearly impossible to do with current data. So I am not a fan of this second condition. Interestingly, Alan Stern, the co-creator of this definition, also didn't like the IAU definition which was voted for in 2006, and for good reasons. Besides that, his definition does make a lot more sense to me compared to the IAU one. Still, despite the problems, a lot of credit should still be given to the overall definition, as on top of the first condition being good, it also doesn't exclude moons from having the status of a planet. So I gave all of the reasons as to why I reject all of the conditions in the original IAU definition of a planet and a dwarf planet. And yes, that also includes rejecting hydrostatic equilibrium because, as already stated, that condition has some strange entailments. Now that I also gave my definition for what counts as a planet, dwarf planet, and asteroid, it is going to be pretty clear what I mean when I say those terms going forward.